Okay, let's continue our discussion. So today we are going to discuss radius of gyration. So let's say we have an extended body here, and this body is made up of n number of particles, and this body is being rotated about this axis. In general, we take this axis as z-axis. So let's say here we have m1, m2, and up to mn. So let's say this is particle having mass mn, this is particle having mass m1, and all other particles are there inside this body. So this is at a distance of rn from the axis of rotation. This is perpendicular distance, and this is r1, and all other particles are corresponding way. So we can write moment of inertia for this body will be m1 r1 square plus m2 r2 square plus so up to mn rn square, or we can write it in summation form like I equals to 1 to n and mi ri square. This is moment of inertia for this body about this axis. Now if we can make an equivalent arrangement for this, let's say we have a particle here, and the mass of this particle is capital M, and this mass capital M is nothing but sum of all the mass of these particles, means m1 m2 up to mn. Or we can simply write I equals to 1 to n mi. And if this particle is being rotated, means revolving more precisely around this axis, and the distance is from here to here, let's say this perpendicular distance is k. So we can write moment of inertia in this case equals to m k square. So if we can represent or make any equivalent arrangement so that entire mass of this body can be considered to be concentrated at a point, and then we can find out what is the moment of inertia in this case. So we will have here a distance square. This distance is called radius of gyration. So we can write radius of gyration. Now we can find out in various cases what should be the radius of gyration. So let me give you a very simple example here. Okay, let's say we have an axis here, and we have two point masses. One is here m, and at a distance of 2r, and another, let's say here, at a distance of 2r once again. So let's say this is, although this is not looking like same, but these two distances we can consider, and the mass is 3m. Now these are making revolution around this axis this way, and this is also making revolution. So what will be the moment of inertia in this case? We can write moment of inertia equals to 3m 2r square plus m times, oh, this one is 2r whole square, and again here 2r whole square. Now we can write it 3m plus m, 4m, and 2r whole square. Now we can compare with this equation I equals to m k square. Let's say we have an equivalent arrangement here, and this is mass 4m, and this mass is revolving around the axis on a path, a circular path having radius k. So we can write I equals to here 4m into k square. And then if we compare this I and this I, because these two are equivalent, so we can say k equals to 2r. So this system has radius of gyration of 2r. So this is for discrete masses here. We can do the same thing for continuous masses or for extended bodies. And while figuring out what is moment of inertia, we will try to obtain this radius of gyration at the same time. So let us move to figuring out what is moment of inertia in different cases for different bodies. Okay, let's take the first example here, ring. So this is a ring here, and let's say we have a ring here. We can say this is one dimensional mass distribution, means linear mass distribution, not exactly one dimensional but linear, around this let's say this point at which we can call center at same distance. Let's say this distance is small r. So we have, let's say this ring is made up of n number of particles having masses m1, m2 up to mn. So we can write here m1 r square plus m2 r square plus up to, if there are n number of particles, mn r square. And in this way we can write r square is common, m1 plus m2 plus mn, and if we are adding all the particles here, means their masses, so we can write the total mass. Let's say total mass is m, mass of the ring is m, which is m1 plus m2 plus up to mn. So we can write I equals to m r square, where m is the mass of this ring and r is its radius. Now hollow cylinder, let's say we have hollow cylinder here. So this is hollow cylinder. So, and we want to obtain its moment of inertia about this axis here. So here the axis is this one. Okay. So which is perpendicular to the plane in which this ring is lying. So the radius, let's say, is capital R, and the mass of this hollow cylinder is capital N. So what we can do, we can just think that this hollow cylinder is an arrangement of n numbers of such rings. So each ring, let's say, having mass m1, m2, and so on up to mn. So the mass of this hollow cylinder will be m1 plus m2 up to mn. Now, if you want to know what is the moment of inertia for this hollow cylinder, we can just add up the moment of inertia of each individual ring here. So we will have m1 plus m1 r1, and r1 r2 all are here capital R actually. So no need to write it in different way. We can simply write m1 r square plus m2 r square and up to mn r square. And again we are coming to a point where we can take this r square common, and then we will have m1 plus m2 up to mn. So this will be the total mass of this hollow cylinder. So we have this much. And what about radius of gyration in this case, and of course in this above case? So here we can say total mass is here and some distance squared here. So the radius of gyration will be r here, and in this case the radius of gyration will be capital R. Now what about this? Okay, so let us consider, here we have a disk which is being rotated about this z axis. So let me draw. This is a two-dimensional circular. Yes, this is a two-dimensional circular lamina. So of negligible thickness. So you may think it as a mass distribution in plane. This is disk, not a ring. Okay. So what is moment of inertia? So if the mass of this disk is, let's say, capital M, and the radius of this disk is, let's say, R, then what will be its mass per unit area? Means, let's say this is a disk, circular disk, of course. So its mass per unit area will be m divided by pi r square, which we can call surface mass density. Okay, so this is mass per unit area. Now, if we want to know what is its moment of inertia, we will have to take integration approach here. And now I'm going to show you how we can proceed. So let me draw it again here, a little bigger. So this is axis of rotation, z axis, and this is the disk. Now you should not be confused about. Okay. So what we can do, we can take a small ring here, let's say here, and its thickness, not actually thickness, but this is, I am talking about this one. So let's say this is y-axis here. This is y-axis. So from center of this this distance is y. So what will be the circumference or length of this rim, this elemental rim? So length of this elemental rim will be 2 pi, and r is here y, radius is y, 2 pi y. Okay. And if you want what is the surface area of this rim, means I want to take this surface area. So what will be the surface area? So this will be circumference times its thickness or width here. So this is, let's say, very small width dy. So it will be dy. Now its surface mass density is this much. So we can write for this rim, this elemental part, we can write a small mass or infinitesimally small mass dm will be this density, which is m by pi r square into 2 pi y into dy. And now I want to know what is the moment of inertia of this elemental ring. So this di, moment of inertia, will be y square into di, mass times this distance square. And now if you want to know what is the total moment of inertia of this entire disk, we have to integrate this thing from y equals to 0 to y equals to r, which is radius of this disk. So let us do this thing. We can do I equals to integration of this di from 0 to r. And then we can write integration of m by pi r square into 2 pi y dy, and of course here y square, this is dm only, so y square. What we can do, we can take constants outside, and yes, of course this is within limit of 0 to r. So we can take this m, and pi will be cancelled out, 2m by r square outside. So 2m by r square outside, 0 to r, and then we will have y cube inside the integral sign, y cube dy. And then if you know the basic integration, you can easily say that this is going to be I equals to 2m by r square, and this is going to be y to the power 4 divided by 4, and limits will be 0 to r. So we can write here 2m by r square into r to the power 4 divided by 4, and minus, if we are putting this one here, it will be 0. So no need to write that. And at the end, we are going to get I equals to 1 by 2 m r square, where m is the total mass of this disk and r is its radius. So here we got what is the moment of inertia for this disk. Now we can extend this concept to get what is the moment of inertia of a solid cylinder. And how can we do this? We can do this for solid cylinder. So we can do, this is a solid cylinder, and we can consider that this solid cylinder is made up of such n number of disks, and each disk has mass, let's say m1, m2, m3, and so on. So adding up all those masses will give us total mass of this solid cylinder, which will be m1 plus up to n terms. And then we can do one thing. If it has radius capital R, we can write its moment of inertia about this axis will be m1 r square plus up to m term, and then it will be ultimately m r square. This will be 1 by 2, and this will be I 1 by 2 m r square, where m is the total mass. Yes, we can write here up to mn, and of course here we can write 1 by 2 mn r square. So ultimately this solid cylinder has moment of inertia of 1 by 2 m r square, where m is its mass and r is its radius. Now let's move to the next let's take a thin rod here. So let's say we have a thin rod here, very thin rod, so that we can consider it one dimensional mass arrangement. And if it has total mass m and its total length is capital L, we can write its linear mass density will be m divided by L. So we can write linear mass density this much. And now we want to know what is its moment of inertia about this axis here. Let's say this is z axis. So we can take the same approach. Let's say this is y-axis because this is a continuous mass distribution as we have done in case of disk. So we can apply the same concept here. Let's say this is y-axis. So we can take a small elemental mass here, and let's say this mass is dm, and at a distance of y from the this origin or this reference point here. So, and its total length is L, then from here to here, it will be L by 2. And this is, we are moving opposite to this positive Y. So, here the length will be, not length actually, this point, this coordinate will be minus L by 2. So, now we can continue. We can do one thing here. The small moment of inertia of this element about this axis will be dn y square. So if we want what is the moment of inertia of the entire rod about that axis, we can write I equals to integration of di from the limit here starts with minus L by 2 to L by 2. And then we can write, let me bring little bit upward here. So we can write it integration minus L by 2 to L by 2, and dm will be how much? It's, let's say its length is, this element has length is dy, very small length. So dm will be this linear mass density times this length. So this dm will be mass per unit length into this length dy, and then we have to multiply it with y square. So this m by l is constant, of course. So we can take it outside m by l here, and this will be minus l by 2 to l by 2, and then we will have here y square dy, and of course we can do once again the same way. I equals to m by L, and this will be y cube by 3, and then we will have here L by 2 here, lower limit minus L by 2. So we can write it m by L, and then we will have here L cube by 24 and minus L cube by 24. You can do it by yourself. If you know that x to the power n dx will be x to the power n plus 1 divided by n plus 1, and if there is some limit here from x1 to x2 or something, we can apply that limit here. Lower limit is x1 and upper limit is x2. And then what we need to do, we need to put, instead of x, we need to put upper limit, and then minus, we need to put lower limit in place of x. So this is what I have done here. So m by L, and here it will be L cube and plus, this is going to be plus. So 2L cube divided by 24. So ultimately it will be L cube divided by 24, and here 2L cube divided by 24. So we will have m L square by 12. So we can say that for a thin rod, we will have moment of inertia about an axis which is passing through its center and which is perpendicular to its length. So this moment of inertia we can write I equals to m L square divided by 12. This is what we can do. Now we can extend this approach to get the, yes, a rectangular lamina, moment of inertia for a rectangular lamina. Okay, let me show you how can we do that. So let's take, I guess it is sixth one. rectangular lamina. So what we can do? We can consider this rectangular lamina as a system of various linear mass distribution here, just like thin rods. Here we can consider that. So let's say there are n number of such thin rods, and we want to know what is moment of inertia for this rectangular lamina about this axis. Let's say this axis is Z. If its length is L, so for a single rod here, we have just obtained that for a single rod, let's say it's a small, not exactly a small, but yeah, let's say something here, I1. Moment of inertia for this first rod will be m1 L square by 12, and up to n it will be, let's say, in mn, the mass of this, or of course we can say if these are identical, then we can write only this m all over. So at the end, what we are doing, we are just summing up the moments of inertia for all these rods. So at the end, let's say this lamina has mass of something m prime. So at the end, we will get I equals to m prime L square by 12. Why I am saying that? Because if you are adding all these moments of inertia for individual rods here, what we have considered that this system is made up of n number of rods having length L, and this is what the length of this side of this lamina. So in that case, we will get this much moment of inertia. And what about if you want to know what is the moment of inertia about this axis? So for this axis, we can find out in the same way. Let's say this is y-axis. So in case of this axis, if this length is something, let's say b, so about y-axis, this is about z-axis. About y-axis, the moment of inertia will be mass of this lamina and this length, which is b square divided by 12. This way we can find out. And remember, these axes are passing through the center of this lamina and in the plane of the lamina. Okay, up to here all good. At the end, I would like you to remember two more things here. Number one, in case of solid sphere, solid sphere, and I am not going to derive it because it will take a concept of double integration, and which you are going to get in the higher studies. So if you are interested, you can visit the playlist containing the topics for IIT JAM or CUET PG, which I am going to upload a little bit later. So this is an axis which is passing through its diameter, and let's say it has mass of m. So in this case, moment of inertia for this solid sphere will be I equals to 2 by 5 m r square. And in the same case, if it is hollow, means thin spherical shell, this will be 2 by 3 m r square. Now, if I'm coming to this point, just a minute here. If I'm coming to this point, and if I'm asking what is the moment of inertia of this rod about an axis which is passing through one of its ends. So if I'm asking what is the moment of inertia about this axis here. So for such type of problem, and of course one more is there. So we have two theorems here, and with those two theorems, you can obtain a variety of situations here, and there you can find out moment of inertia in each and every case. So let me just explain this one first. So here, coming back to a new place here. Okay, so if we have a rod here, thin rod, and we know its moment of inertia about an axis which is passing through its center, let's say this is, and its length is L and its mass is capital N, let's say. So about this axis, Z axis, its moment of inertia is we have obtained ml square by 12. Now I'm going to introduce parallel axis theorem. Parallel axis theorem. So any axis which is parallel to this z axis, we can obtain moment of inertia about that axis. So this is passing through its center or its center of mass. We can say this rod is uniform. Okay. So in that case, if we want what is its moment of inertia to about a new axis, let's say this is z prime. So we can write it as this distance is L by 2. I'm talking about distance. This distance is L by 2. So we can write, if we know the moment of inertia about an axis which is passing through its center of mass, that is Iz in this case, is ml square by 12. So we can find out what is its moment of inertia about an axis which is parallel to this axis, which is passing through the center of mass and at a distance of L square. This will be sum of this moment of inertia and the mass times this distance or length squared. So if we have moment of inertia about this axis, we want to know what is the moment of inertia of the same body to another axis which is parallel and at a distance of this. And if this body has mass m, we can write the moment of inertia as sum of these two terms. So in this particular case, if you want what is moment of inertia about z prime axis, we can write ml square by 12 plus here m L square by 4. This is going to L square by 4. So what we can write here, it will be 3ml square plus ml square by 12 and ultimately 4 by 12, that will be ml square by 3. So about this axis, the moment of inertia will be ml square by 3. And this is valid for any extended body here. As long as we know what is the moment of inertia about an axis which is passing through its center of mass, we can obtain moment of inertia about any other axis which is parallel to this axis. And we know the mass of the rigid body and the distance of this parallel axis. So if you generalize it, it will be parallel axis theorem. So the next is perpendicular axis theorem. Okay, let me write it first, then I'll explain what is it. So perpendicular axis theorem, or maybe axis theorem. Okay, we have just obtained here in case of rectangular lamina. Yes, here we have obtained the moment of inertia of this lamina about this z-axis and about this y-axis, and these two axes are perpendicular to each other. So if we want to know what is its moment of inertia about an axis which is passing through the same point and which is perpendicular to the plane of this lamina. I mean, the plane in which this x-axis and y-axis and z-axis are lying. So let's say this is x-axis in our proper coordinate system. So if we want to know what is this moment of inertia about this x-axis here. So for this, we can use perpendicular axis theorem. So be attentive about these things, what we are taking here. So let's say we have a lamina here in YZ plane. This is a rectangular lamina in YZ plane. And its length, let's say this is length L and its breadth here B. Okay. So there is one axis here which is in the plane of this lamina. This is Y axis passing through its center here. And there is another axis here. This is also passing through the same point, and this is along z axis here. Okay, now we know moment of inertia about z axis will be mass of this lamina times b square divided by 12. This length is b. Earlier we were taking L, and I y will be m L square by 12. And now I want to know what is its moment of inertia about an axis which is perpendicular to the plane of this lamina, or which is perpendicular to the both these axes, and these two axes are also perpendicular to each other, orthogonal you can say. So what it could be, so we can write ix. So this ix will be equal to iy plus iz, this way. So these two y and z axes are in the same plane, perpendicular to each other, and on that plane ix means this x-axis is perpendicular. So if we want to know what is the ix here, we can just simply add this thing, and then we will have m times 12 and b square plus l square here. So in general, we can say if we have any two-dimensional thing here, and let's say we have two-dimensional thing here, and one axis is here, we know what is moment of inertia about this axis, and another axis is here. Let's say we know what is moment of inertia of this body, this lamina about this axis. Then we can find out what is the moment of inertia about an axis which is perpendicular to both these axes. So in this case, we can write Iz equals to Ix plus Iy. And you should be careful about this. These two axes are, means X and Y are perpendicular to each other, and these two are lying in the same plane. And the third axis about which we are deriving, this axis is perpendicular to the plane in which this y and x axis are lying. So in general, if we are using this thing, this is perpendicular axis theorem, which we have already mentioned here. And this is example. So this is all for this class. In the next class, we will continue our discussion of system of particles and rotational motion.